My name is Johan Angevaren on behalf of the XENON Experiment here on PyHEP. Whereas we're actually not doing so much high energy physics, but actually low energy physics because we're doing a rare event search. But nonetheless, let me explain a little bit how we use Python in our experiment. Our experiment consists of many institutes all around the world, and our aim is to detect dark matter. To that end, we have here our time projection chamber filled with liquid xenon, where with one day we hope to find a dark matter interaction. It's located in Italy, which you see here on the right side of the figure. Now, let me explain a little bit how this experiment works. So within this vessel, we have liquid xenon, and if a particle interacts, we create a first scintillation signal, which we call the S1, and the electrons that are freed in that interaction are drifted upwards because of an electric field creating an S2. And with those S1 and S2, we have all the information we need to do the physics, which may one day allow us to find dark matter. Now, of course, we need to reconstruct this properly, and to that end, we have 500 light sensors, PMTs, both at the top and the bottom of this detector. And each of these PMTs is continuously being read out. So they measure pulses over time, and we do this. This is the only place that where in the software stack C++ comes into play. We do this with readx at a rate of about 50 megabytes per second. So let me stress again that each of these channels is read out in a self-triggered way. That means that there is actually no trigger globally applied to this data. Nevertheless, we're able to store all of this data because we're a rare event search. So all of this data is making it to disk. And from then on, it's Python only. So in order to reconstruct what went on in the TPC, in our detector, we need to first group all these pulses together to make the S1 and the S2 peaks. If we then have those peaks, we again have to group them together to get the real event, what happened in the TPC. And with that, we can do the physics we want. Now, let me showcase how our software works. And rather than talking about it a lot, I'd rather start off with a demo. I must apologize in advance that I didn't upload the notebook because of the amount of data that's created. It would just take a long time. But all right, so in the following demo, we're gonna look at how our software would enable us to look at the detector live while we're, for instance, calibrating it with a radioactive source, a krypton source, and we're just gonna look how we can use this software to look at the data. And next, I will also focus on if we have the data, how we can do multiple analysis at the same time. But let me just start off with a demo. So imagine I'm now on my own computer starting up a fake DAQ, which is processing the data live. While we're doing that, we can already look at the data and see what's going on. If we look inside this graph, we see for some energy ranges how the event rate is building up. The different lines indicate different energy ranges. We can also see the different types of peaks. So we have these S1s, which are very sharp, and S2s, which are very broad. And this is all happening live on my own machine. You, by the way, can also look at how much each of the channels is seeing. And this can go on while we're doing a krypton calibration to actually see live the development of a radioactive source building up. Now imagine that you're an analyzer, you now want to look at this data. Krypton has 3 characteristic peaks, which you see over here. There's 3 of these peaks characteristic for Krypton. However, an analyzer notices that there's also a lot of stuff at the low energy and comes up with a brilliant idea to get rid of this low energy stuff by changing a configuration for the number of PMTs needed in order to define a peak. This analyzer changes the configuration that is involved, which is this 50 it changes it to saying that each peak should be seen by at least 50 PMTs. And while it's doing that, it's asking the software, okay, well, then just give me the new data as if we were processed with this setting. And within just 18 seconds, we have reprocessed this data. And of course, we are targeting this low energy part of the data. And now I would like to show you that there is also something interesting going on if we look at the amount of data we have processed. Don't want to go into details of what all this data is, but if you now look in our process data folder, you see actually that there's 2 copies of peak basics, whereas just only 1 copy of records and pulse counts. I will come to that in just a moment in the rest of the presentation. But in order to, we actually also do this online processing live on the entire XENON data. So that means that we're at the DAQ level already doing a full reconstruction of our entire data chain. So going from the raw signals all the way to these events. And this comprises doing the baselining, finding the hits, doing the peak finding, and actually this peak finding you might call a trigger, as before that we don't actually have a trigger other than the self-trigger of the digitizers. Also, we do position reconstruct using neural nets using TensorFlow. We apply corrections. Everything is happening faster than as fast as the data is actually coming in. And to be able to look at this data, we also ship a part of it into a Mongo database, which allows people to actually look at this data online as data is being collected. So within 30 seconds, you can anywhere in the world see the fully reconstructed data as it was detected in the DAQ. And we actually made it even easier for people that you don't even have to open a terminal. You can just ask via Slack for the latest status report. So how do we do all this? Because I said this is all done in Python. How we were able to get this all doing all this reconstruction as fast as the data comes in? Well, of course, what you need to have is performance. And when we were upgrading from XENON1T to XENONnT, we also upgraded our software. So in the old days, we were able to do just 200 kilobytes a second per core. Now with the new software, which we call Strax, we're able to go much faster. So let's look a little bit deeper into how do we actually get there? How does this work? The answer is this Strax, the streaming analysis for XENON. And our software is divided in this generic Strax framework and the XENONnT specific Straxon framework. So in Strax, we have all the generalized and optimized code. As I will explain a little bit later, we're relying heavily on numpy and numba to make all this stuff fast in Python. The detector specific software, like choices, how many PMTs you need in order to define a peak, is all stored in Straxon. Both are, of course, relying heavily on continuous integration, and the core code is public, whereas analyses and detector specific conditions are, of course, private. All right, so let's look a little bit deeper into what is our goal for this software. So the goal is to get from these raw PMT traces to the events. And in the meantime, we also, of course, need to cluster those PMT traces correctly in order to build the peaks. And we have chosen to go for a tiered data structure and a modular processing framework. So how does this look like? Well, at the lowest level, of course, we need to read out what the DAQ spits out. So as I said, we have a reader software in C++, which just dumps the data as it comes out of the digitizers to disk. Then when we start reading this in with Python, we have a DAQ reader, which is able to read the format and convert that to this to the Python format we are using later on. We then have to process the pulses to get the peaks and events. And as you can see, and as you can imagine, that at the lowest level, all these raw PMT traces, there's a lot of data there. So this is typical for a 1 hour run. However, if you go further up in the chain, you're doing the triggering, you're doing the triage, you're making selections, the data becomes much smaller very quickly. And in the end, when we're talking about events, we're orders of magnitude smaller in size. And by the way, illustrating here all the processing steps along the chain, which we call plugins, as Lego blocks, because we went for a very modular approach, which makes it very easy to interchange one of these plugins. For instance, in the demo I just showed, there wasn't actually a DAQ reader, but instead there was a simulator plugin which simulated the data. Now we wanted to know how we make this fast. So for that, we need to look a little bit further into how is the data shared in between those plugins. And the answer is that, for instance, when we're looking at pulse processing, we look at a given chunk of data. We organize all of our data in time intervals, which we call chunks. So there's a chunk of data which is being processed by the pulse processing, and after it's done with that, it will send it up to the next plugin to be processed there. We can do multiple chunks at the same time, here illustrated with the conveyor belts, because we are able to multi-process all this. Now, each of these chunks is organized in a tabular format. That means that the arrays are of fixed length. We use numpy structured arrays for this, and everything is a fixed length. However, this may not sound like a very intuitive choice, for these S1s are very short signals. So if you're talking about a fixed buffer length, such an S1 signal easily fits into this in this buffer. However, S2 signals can be very wide, up to microsecond long. And that means that we sometimes need to split all these raw traces into multiple buffers, thereby introducing some extra bookkeeping. However, of course, with this extra bookkeeping, we're later able to reconstruct one S1 followed by an S2. But that may not sound like a logical choice, given that you know that we have such different data for S1s and S2s. However, it is what makes our software fast. Because of this, and because of the great features from numpy structured arrays and numba, we're able to do all this processing live in Python. So using just-in-time compilation, most of especially the low-level software is all very much relying heavily on numba. And because of this tabular format, we're able to do this auto-vectorization, which makes it really fast to go through all of this data. Now, there was also a second question, which I already briefly touched upon in the demo, because now that we have a very nice fast framework, we of course want to use it for the many different types of analyses we can be doing in XENON and TON. Therefore, I'm going to zoom in a little bit more onto these plugins, and I've of course been very much making this a lot simpler than it actually is, because actually each of these Lego blocks shown here can consist of multiple sub-algorithms needed for the processing. And each of these plugins has a fixed set of attributes. So it has some options, it has a version, it knows what kind of Lego block it was built upon, and it also knows what kind of data it provides. Then, of course, it uses the highly optimized code we have in Strax in order to do all this fast. Because if we're thinking about the experiment, we might want to change one of these options, as I showed in the demo. And if this is happening, we, of course, still want to know what data is belonging to what plugin, what options were used. So for that, we use these incomprehensible hashes, which you might have already seen in the demo. So all of our data has a given run number, the kind of data it is, and also this hash, which is behind it. And that hash is an encoding using hashlib of the entire ancestry on where the data was built on. For instance, if we look at peaklets, it's produced by a plugin, which we call peaklets, which has a given version. It has some options, and it's built on top of the records, which has a similar format again. Now, this entire dictionary of how things were built up is encoded in this hash. And now if we want to change something, for instance, we want to use a different gain model, and you ask for this, the data which belongs to this, the ancestry changes, and therefore we use a different hash for encoding this data. However, of course, the data which is below that, the records, where we actually do the pulse processing, doesn't change when we change something which is associated to peaklets. Therefore, in the example I also showed, the records were actually only produced once, because we were only asking for one configuration. The higher level data, where we changed the configuration, was produced twice. And this is how we allow for partial reprocessing. And of course, if you think about the stack of how we build up our data, you mostly want to do this for high level stuff, where actually most analyzers are working on anyway. If you change something very low in this processing chain, of course, you then need to reprocess a whole lot of data. Now, this may sound complicated, but we try to make this easy for the average user of our framework, because there's always so many different needs, but there's only a limited number of developers. So to make things simple and robust, we set up everything like these options and these plugins for a given search. For instance, if you're talking about XENON1T data, you might want to have a specific set of options. When you're working on detector simulation, you're maybe having some different options. But everybody who's looking for XENON data, position reconstruction, or dark matter, or anything else concerning XENON, these people all want to use the same options. And we bundle those options in the context. The context is a centralized object within our framework. So also when you're changing only one of these parameters, you're still able to use the Anton context, because maybe you've only changed something very high up in the event level. This context is talking to all the parts we have been discussing so far. So when a user asks the context for some given data, the context will first compute, all right, so with this data you're asking for, how does it work together with all these plugins and options? Do I actually have the data stored already? If so, it will return it, but if not, it will just go all the way down in the data chain to find where it first finds some data, like the lowest level data, that is consistent with what the user asked for. And then it will start processing it and return it to the user, as well as store it to disk, so that when next time or someone wants to use it or the user wants to use it, it's still there. All right, so XENON, we have gone for a data which we organize in chunks, so fixed time intervals, and in a tabular way we organize our data in order to make processing fast. We're using modular design of our algorithms and a tiered data storage approach, where the high-level data is much smaller than the low-level data. Because we keep track of the entire ancestry of data, the entire lineage, partial reprocessing becomes very easy. And given the speed of our framework, people actually do this quite a lot. So with this, we get from PMT signals to events in as fast as we can actually take the data. And all what I've been telling about is not only limited to time projection chambers, so where we are looking for dark matter. For instance, our veto systems are using the exact same framework to talk to the PMTs used for instance, the neutron veto and the muon veto we use for tagging backgrounds from neutrons and muons. So with that, I would like to conclude. Thanks so much for your attention.
Thank you very much, Joran. And you actually have a handful of questions on Slido. I've dropped a link on the chat. I don't know if you want to share that to go through the questions.
So the first question, you can see my screen, right?
Yeah, that's great.
So what I was just showing wasn't real data, but actually it was based on simulated data, but the overall real data looks really similar, and also the workings are exactly the same. Right there. The next one. Is any of the general software used outside the XENON community? Good question. So the general software at some point was also, there were some searches by Nexo to see if they could use it for their MC chain. I must admit that I'm not fully up to date whether they're actually using it. But also small scale experiments, like for instance, we have here at our institute at the lab, use the same general software, but it only has 2 PMTs. So those kind of very specific things are changed, but the general software is also used for these small experiments. There are various dark matter experiments out there. Are these collaborations doing as we are in high energy physics and trying to share as much a dark matter ecosystem as possible? If not, why? Well, that's a very good question. So our main colleagues are from the US and from China, and we don't use the same kind of analysis software. We are at this moment at an entire different paradigm, whereas we are only using Python for all the processing. Our US colleagues have gone for C++ all the way, and it's just a very few last bits where they are using Python. So already there, it's completely different. And it's also dictated a little bit by the design choices made in the DAQ. Whereas we have gone for the design choice to do everything in software, our colleagues from the US are doing a lot of FPGA triage already very low level at the DAQ. Maybe for the next generation experiments, we are trying to get together much more closely, but at this point, we're quite diverse in these ecosystems. I hope that this has answered your question. So it wasn't real data, it was simulated data. Do you share the cache lower level output between collaborators or between institutes? How is this managed? Yeah, good question. Maybe I have a slide on this. Let me see. Okay, no, unfortunately I don't. So it's a good question though. So all of our data is shared between our own collaboration. So this raw data we are getting from the digitizers themselves is so massive that it is very hard to store in one place. So for that, we send it out to the data storage facilities. It's very easy to download it, but only on request. Somewhere intermediate, so maybe I can share my slides again. At the intermediate level, when we're talking about peaks, this data is shared between everyone and can be opened. And so when we do a reprocessing, we are also mostly focusing on this aspect because this step is so fast and so easy that analyzers can do it just on themselves. And we're having one centralized analysis software facility where all of this is stored and everybody can do their analysis. Now I need to get back to the question. Do you exclusively use Python for the high-level analysis, or is it the usual mix-up of C++ framework for inside the experiment? So we only use Python. everybody uses Python for the high energy, for the high level analyses. So there's no mix up between C++ and C. There's no real war going on there. It's only for our simulation software that, for instance, GN4 and stuff is coming into play. But for the high level analysis, it's only Python. How is the performance of the US C++ framework compared to? I must admit that I'm not familiar with the. Okay. So you're talking about our main colleagues. Yeah, very good question. I have actually never tried using their software, also because their software isn't publicly available. Otherwise, I would be very interested in trying this out. I wouldn't be surprised if our framework is doing quite well compared to them, but yeah, I must admit I have never used their framework, and I also cannot because it's not open source. Are there any open science initiatives in XENON and TON? So you would mean the sharing of data in XENON and TON? Unfortunately, as far as I know, there aren't any initiatives to make the data itself publicly available. All of our software is, and we highly also encourage people to be able to run these tools. For instance, you can very easily run our simulation software yourself. But as far as I know, there aren't any initiatives to share like the low level data. It's also quite hard because it's so much data. Oh, there's questions keep on coming, which is good. Yes, sharing data and tools. Yes, I agree on that. How do people that have to deal with GN4 and C++ find it if they're now more used to getting work in Python for the rest of the experiment software? Yeah, it's a good question. There are many people actually are completely fine with having this mix-up, but there's also a bit of a shared, of distributed tasks, right? So the people who do most of the heavy GN4 simulations usually aren't the same people doing the very high-end analysis. Sometimes they are, but most of the times they're different people. And we just work together in order to bring everything together. So so far there's no real struggle there. It's also because we have been using Python so much that it's kind of a given. It's mostly for new people entering our collaboration, which sometimes have to get accustomed to using Python in this way.